Everyone. Terima kasih uh, telah bergabung bersama kami pada webinar pada hari ini yang berjudul Empowering Predictive Maintenance of Electrical Rotating Assets. Saya Muhammad Sidik di sini sebagai moderator. Pada sesi hari ini akan memberitahu agenda pada webinar siang hari ini. Yang pertama yaitu perkenalan CV pemateri, dan kedua sesi pemaparan materi oleh narasumber kita, dan yang ketiga sesi tanya jawab, di mana untuk peserta yang ingin bertanya, silakan ketikkan pertanyaan di kolom komentar atau chat selama sesi berlangsung, dan kami akan memilih beberapa peserta yang beruntung yang telah bertanya untuk diundi mendapatkan dua hadiah. Baiklah, langsung saja. Saya akan mengenalkan narasumber utama kita pada hari ini. I would like to introduce our speaker today. Uh, he is Kristians Cernevics, product manager and scientist with blend expertise in advanced materials, SV discharge, and computing intelligent condition monitoring system. Christian holds a PhD from EPFL Switzerland, where he developed high throughput tools for nanoelectronics and contribute to AI-driven research in condensed matter physics. He currently works at Quartzteq GmbH, leading the development of software and hardware for industrial monitoring solution, and his background spans academic research in material science, electronics, signal processing, as well as consulting on deep tech and vendor strategy. Baiklah, tanpa berlama-lama, mari kita dengarkan pemaparan dari Kristians Cernevics. Please join me in extend a warm welcome to Kristians Cernevics. Christian, the time is yours.
Thank you a lot for the very nice introduction. Let me set up my presentation and let's start. Okay. Yeah, can you see the presentation? Everything is okay?
Good, everything is okay, Christian?
Okay. So thank you again for the very nice introduction. I'm very happy to be here, and thank you, Intan and Sidik, for inviting me to give this presentation. And I'm very surprised and very happy to see so many people joining. So I'm excited to share a bit of the knowledge we have and a bit of the know-how of how to empower the predictive maintenance of electrical rotating assets through condition monitoring. So let me start with what I'm going to go over this presentation. I'll do a quick introduction of Quartzteq, of the company I'm representing. Then I'm going to move on to condition monitoring, explaining you what condition monitoring is, a bit of theory behind the partial discharges, the different types of monitoring online or offline, the types of sensors you can use, and then the two additional types of measurements, such as the air gap flux, shaft voltage, and in the end, about how we can integrate these monitoring systems already in the existing systems in plants. And if I have time in the end, I'll also want to touch on some real life case studies to see how, what is the real life impact on condition monitoring on a real machine. So without further ado, let me briefly introduce you Quartzteq. So Quartzteq is a Swiss company, part of the Quartzteq group that is based in UK, in Rugby. Quartzteq is specialized on the development and manufacturing of innovative condition monitoring systems for rotating equipment. Sorry, I think I hear some noise. Yeah, okay, now it's okay. Part of this group, we have more than 100 years of heritage and experience in different fields. First of all, it's the electrical engineering, coil design, and also mechanical, so welding and fabrication. So when we design or condition monitoring systems, we try to combine all this together to provide a system or a tool that is, that has a real life application and has been inspired by the whole knowledge we have in our group. As I mentioned, the Quartzteq and Quartzteq legacy goes back almost more than 100 years, back to the British Thomson Houston Company, established in the end of 19th century. And then Quartzteq, as it is right now, was established in 2007, once a management buyout through a Segalek, which was divested in different parts of the company. And then since then, Quartzteq was acquired in 2011. And yeah, we can really see this very long heritage of the company and a lot of experience acquired along the way. Mainly, Quartzteq is specialized on condition monitoring. So we offer monitoring solutions, but group as a whole, Quartzteq as a whole, has also the expertise, knowledge, and know-how on the terminal boxes, on protection and testing of the devices. So there's a lot of interchangeability between what Quartzteq does, what Quartzteq does. So there's a lot of exchange of the knowledge between the different parts of the group. And also, yes, Quartzteq also provides some OEM spares. The main markets we are focused on as Quartzteq is power generation, oil, gas, and petrochemistry, as well as general industry, for example, steel manufacturing. And then group as a whole, Quartzteq as a whole, also has entities that specializes on utilities, on commercial and services, as well as the renewables, and also some parts are specializing on marine and defense fields. Quartzteq distributes our solutions through an official network of distributors. Mainly, we're located in Latin America, Europe, and Asia. So altogether, we have 16 official distributors. And in Indonesia, we have a very good working relationship and a partnership with Tiara. So for all your needs, for your rotating machines for condition monitoring, Tiara is the place to contact. And just to give you a very quick overview of the type of products Quartzteq offers in the very beginning, and then I'm going to go into the more detail to explain why to use a specific type of product, what are the advantages, disadvantages. So essentially, we're developing condition monitoring solutions to protect and assess the health of your rotating machines. Mainly, we're specialized in partial discharges, but also on the shaft voltage measurements and air gap flux measurements. We offer both online and offline monitoring solutions. So depending on your needs, depending on the accessibility of the machine, on the schedule of the shutdowns, we can find different solutions. And we also offer sensors and modules that are capturing this data. So let me now just take a step back and maybe give a very general overview of what is condition monitoring, why do we actually need it, and how does it help us in the future if we employ condition monitoring. So as we all know, all machines will be affected with time, with mechanical stress, with temperature, with the environment it operates. So depending on the machine, depending where the machine is, and also depending on how well it is regularly repaired or maintained, all of these machines will gonna have wear and tear. So the health of the machine is gonna decrease gradually. So condition monitoring essentially is like a doctor, so that this doctor can monitor the health of the machine continuously. So either we do it a permanent installation and we monitor the health all the time, or we do periodic checkups, like you would go to a doctor and periodically check up the health. So condition monitoring then consists of sensors, first of all, that can capture the data, and tools that detect this and collect this data. Afterwards, this data can be analyzed to identify trends, anomalies, thresholds of how good the health is, how far we can actually go. And then the main advantage here is that the maintenance of your rotating machines can then actually depend on the condition. So if the condition is good, maybe the maintenance can be postponed. So essentially, we want to optimize the time spent on the machine being online and not being offline. And condition monitoring is a great tool to actually do that. So here, I put down the key benefits of implementing the condition monitoring on your machines. So first of all, like I said, it's determining of what is the health of the machine at this particular moment. We can also then increase the reliability and availability of the assets, because we know if the machine is healthy, there's a very low chance that something bad will happen and there's going to be a failure. We also minimize lost production time in that sense. And like I said, we can postpone expensive maintenance. If the machine is in a very good condition, maybe the maintenance can be pushed on at a later time. This also allows us to plan outages better. If we know that multiple parts of the machine are maybe approaching the maintenance time, maybe we can schedule it earlier or schedule it at the same time that we can do the repairs. And this allows just in general to plan the outages better, to plan the work better, and most importantly, also prevent catastrophic failure. Because if we have the data, if we know what is the health of the machine, we should be able to spot before these catastrophic failures happen. We should be able to spot the alarms or some of the anomalies that are happening with the characteristics of the machine. As I mentioned briefly in one of my first slides, that there are essentially two main types of condition monitoring. One is online. So data is collected, the normal operation of the machine. It needs the installation of sensors. So the sensors are installed once the machine is off, but once it's back on, we can then capture the data and analyze it. On the other hand, offline monitoring would be performed once the machine is off. This would happen periodically during planned shutdowns. And usually you would use a portable equipment and an external high voltage source to then do this kind of a type of condition monitoring. And the offline monitoring and online monitoring, I'm also going to explain a bit of the differences and pros and cons each of these types of monitoring has. To give you an idea about the health of the machine and the types of problems we can expect, there's a very nice paper that collected the data about multiple failure mechanisms in motors. And what was found out that 63%, so more than a half of the failures happened in the stator windings. Then the next ones were rotor windings and bearing, coupling, and shaft. So altogether, almost 95% of failures, so these three big chunks happen in the stator, rotor windings, and then bearing, coupling, and shaft. So this gives us already information of what are the key parameters that should be monitored. So first of all, we need to monitor how the stator winding is doing. We need to monitor how the rotor winding is doing. And then we need to monitor what is happening with the bearings, with the coupling, and the shaft. So if we cover all these three parameters, if we monitor them, we can be fairly certain about the health of the machine. And this also gives us essentially the idea of what kind of measurements we need to do. So to start with the first one, partial discharges. So partial discharges are related to the stator winding failures. So this is the most common type of failure, and this is also the most common type of condition monitoring. As I mentioned before, machines are always essentially exposed to external stress. So either it can be thermal stresses, increased in temperature, decreases in temperature, electrical stresses. It can be also ambient stresses. There could be some moisture on the machine, or you can also have mechanical stresses. So something is not fixed in a place. There's a lot of vibration. And all these issues can lead to defects in the machine. You can have vibration, you can have broken conductors, contamination, delamination of the insulation. And all these problems then will emerge as a partial discharge. So you're going to have partial discharges inside your machine. And this is a bit like a circle, like a snake chasing its own tail. The more issues you have in your machine, the more partial discharges you're going to have. And the more partial discharges you're going to have, the further decrease of the health of the machine is going to happen. So what are these partial discharges that I was just telling you about? So first of all, it's an electrical discharge, and it is a partial discharge between a conductor and earth. So here, if you imagine that one of the plates here is a conductor and another plate here is the earth, what we can see is that the insulation should prevent any charge going through. However, if the insulation has a gap, so in the red, there is a void. So instead of an insulation, there is, for example, an air gap. What can happen is that through to this air gap, you can have a discharge. Once particularly high voltage between the plates has been reached. And to give you an idea, the high voltage here we're talking about is around 3 kV on the millimeter. So if your machine is rated at 6 kV, gaps as small as half a millimeter can already give you partial discharges. And when these discharges happen, they can often essentially increase this gap because more deterioration of the insulation layer will happen. So what type of partial discharges are there? Usually we classify it in 3 types. So first of all, those are the internal discharges. So for example, here you can see it's a slot discharge. So there's small gaps in the slot where electrical field can reach high values, and then these small gaps are then transversed by a discharge. And this can lead to some serious consequences. So if this is not spotted, which it's usually not because it's internal, you have like quite high degradation of the insulating material. The second type of discharge is the external surface discharge. So this happens on the surface of the insulation, so such as surface tracking, and usually this happens due to the surface contamination. So the external or surface type discharges can actually be corrected a bit more easier. They can be spotted a bit more easier because you can really see the damage that it's done. It's on the outside of the machine or on side of some part of the machine. And this can be remedied by a thorough cleaning process. So by cleaning the machine and keeping the maintenance of the machine, this can be in some way remedied. And finally, there are also corona discharges. These occur in the gaseous atmosphere around the high voltage conductor. So anything with sharp turns, pin-like extrusions, you might have these corona discharges. So why do we need to monitor? The main reason here, as you saw before, is that, for example, for the surface discharges, it's possible to sometimes spot it by eye, some of them, corona discharges as well. However, the most destructive are the internal discharges that are often hidden from the naked eye, so you cannot really see what is happening inside your machine, if these discharges are present or not present. So for that, you need to monitor them somehow, to know what is happening inside the machine, to know if you have these dangerous discharges. So partial discharge is a symptom of insulation problems, small gaps, small shifts, where there is air between the two conductors and discharges happen there. Increasing PDs gives us indication of how bad the insulation is. And by reviewing the data, we can also try to pinpoint, what kind of discharge it is, where the location of this is, before we need to enter an outage. And as I mentioned before, all electrical systems above around 3.3 kilovolts will exhibit some form of PD. For machines of 6.6 and higher, you would have enough electric field strength to actually cause serious issues. So to just give you an example, here, you can really see how the insulation has been degraded between the coils here. And in this case, it is really visible, these kind of types of discharges. So you don't want to get to this point. You want to already identify it much faster. For those who have a bit of chemical background, essentially how this degradation happens is that once the PD happens, there's a high electrical voltage discharge in the air. Air contains oxygen molecules, and with this additional charge, actually ozone is made. So ozone is a radical that is very, very reactive. So if ozone touches something else, a chemical reaction will happen. It can produce acid from water and nitrogen available in the air. It can produce aluminum, silicon oxides, iron oxides to create rust. So all these compounds are, in the machines or around the machines. So you're going to see these type of chemical reactions happening, and then degradation of your material. And you can even have, if you have copper parts, you can have toxic copper salt made from ozone interacting with copper. So I hope I convinced you that partial discharges are important to monitor. Now the question, I think, is how do we actually monitor? Because we have different types of machines, we have different setups, we have different environments for these machines. So there needs to be a way of how to detect these partial discharges. And they are happening all over the machine, so it's impossible to directly measure or capture one particular discharge. And instead, what we can do is different types of methods. So you can have chemical methods, you can have optical methods, acoustic methods. Each of these have its own cons and pros, and one of the most widely used methods is an electrical method. So what we do is we measure high frequency voltage spikes at the terminals of the machine. So they look something like the graph on the right, where the voltage spikes up. And what we can do is then we can integrate these voltage spikes to get a charge, a value of charge. And then this is essentially standardized by the IEC standards. So QM and QAP charges then can be compared between different machines. So this gives us a nice quantitative way of how we can actually capture the magnitude of the PD discharges. So usually the systems would provide you two different ways. So first of all, it's the PD trend. So how does the magnitude of discharge increase with time? And the other one would be a PD pattern, which would tell you the type of defect that is happening in your machine. So if we look on the right on these three graphs where you have the PD patterns, each of the points is a discharge that I showed you in the previous slide. So it's a spike in voltage. So after some period of time, for example, 10 to 30 seconds, you acquire all the thousands of discharges that are happening in your machine, and you plot it on the y-axis, you will have the charge, and on the x-axis, you will have the phase of the electricity of AC. And from there, you can now see how serious the damage is in your machine and what type of damage there is in your machine. Once from this graph, you get your QM value, which is just a statistical value of the charge, a characteristic charge that is being discharged in your machine, we can plot it with time. Usually for new machines, this can be quite high up. It will go down. It will reach a trend, a baseline. And then for many, many, many years, the baseline is going to stay almost the same. So it means that the insulation is not really changing or deteriorating that fast. However, there's going to be a point in time where there's going to be a problem with the machine. And what will happen is only a few months, maybe a couple of years, where these discharges will grow very fast. And this is the point where you need to catch, you need to know, before the problem goes very, very bad, you need to catch the condition of your machine. So if there is no condition monitoring and, for many, many years, everything has been right, you reach this point and you don't capture that now the PD discharges are happening much, much more, and you don't see it because maybe your maintenance only happens once or two times a year. So that's why as well another reason why condition monitoring is necessary to help your asset health. So the best practices of analyzing once you get your data is, first of all, to look at the magnitude of your discharges. This will vary between different machines, but something around below 5 nanocoulombs, below 10 nanocoulombs is considered to be in a good condition. Anything above that, you might need to start to investigate. The second part is the partial discharge trend I showed you before. Do we see if the trend stays the same, or do we see an increase? If we see an increase, what is it that we can do? Do we need to schedule a maintenance? Do we need to do rewinding? Do we need to cover maybe some of the insulation? And then finally, these questions can be answered by looking at the PD patterns. So experts who know how the PD patterns look for different type of defects then can suggest you what needs to be done on the machine. And here to show you a real case. So this was done with a mobile tool. Essentially, on July 2013, a first measurement was made, and the partial discharge was here determined to be somewhere around 1 nanocoulomb. So this is still acceptable levels because all the machines will have some type of partial discharge. However, what is important is what happened after 6 months. So after 6 months, we saw that it increased from 1 nanocoulomb to 2 nanocoulombs. And generally, the rule of thumb is that if your partial discharge value doubles during a year, so this was even shorter than a year, it means you might need to investigate a bit further. So what was then decided in January is that the next measurement is going to be made a bit earlier. So it was made in the beginning of May. And what they saw again is almost again a double increase. And at this point, Quartzteq suggested the motor to be stopped before catastrophic failure, because now we have reached the point where the partial discharges grow very, very, very fast. So it means that the machine health is deteriorating very, very fast. So this was a type of measurement that helped us predict that the machine needs to be switched off and repaired. And just before I go further, this previous measurement was made online. But like I said, you can do both online and offline measurements. And in the next slides, I'm going to introduce a bit more about the types of measurements you can do. The main thing that differs is that online measurements are showing the PD discharges happening while the machine is operating. So it's going to show you all the PD discharges through all the stresses, temperature, mechanical, ambient. However, offline is only going to show you some electrical stresses. But once again, depending on your situation, you can do both online and offline. And our suggestion would be, those are complementary methods. Some discharges can be better captured on offline. Some can be better captured online. So the best would be to use them both. So now if we go and discuss the online monitoring, what we can see from the Quartzteq offering is that we offer two types of online monitoring systems. One will be an installation, a permanent installation in the plant for a particular machine. So we call it the LiveView PDA. And the other one is the LiveView mobile tool, which can then be used periodically. So it's not installed permanently, but it still needs the installation of the sensors on the machine. So you could have multiple machines with sensors, and then with LiveView mobile, you go there periodically and measure the discharges. With the PDA2, you can measure it continuously. So it's always on, it always gathers the data. So it gives you a bit better representation and doesn't need the movement of the equipment. So the PDA2 is essentially a small computer that you can put it somewhere near the machine. It's a permanent online monitoring system with automatic measurements. So periodically, automatic measurements are going to happen every couple of hours. This tool gives you multiple access points. You can access through an Ethernet, USB, analog, Modbus, or Wi-Fi. So many, many different options of how you want to access the data. It does measurements simultaneously on the 3 phases. And it also has filtering options for noise reduction. So noise reduction in partial discharges is a very big topic because what you want to see is just the discharges, not the noise. The PDA2 also gives you the option to store the data, so you can see what has happened with your machine over a period of time of months and years. And then it's compatible with the Quartzteq sensors we provide, but also many third-party couplers. So if there is already some sensors installed in the machine, it's very likely that you can install a PDA2 and gather the data from these installed sensors. The PDA2 is also adapted for the hazardous area, so it's EX certified. It can be installed with a particular type of sensors called Rogowski coils, which are also EX certified. So it's rated and certified to operate in the EX Zone 1 hazardous area. So it's a very similar tool to the one in the previous slide. However, it's you can see it's enclosed in an EX box. And then finally, this is the LiveView mobile solution. So the one where I showed you this real case, the measurements were done with this mobile solution. Essentially, it's a portable lightweight solution, comes together with the laptop, with the calibrator, with everything you need to perform these measurements. You can simultaneously, again, monitor the 3 channels. Again, this would need sensors to be installed in the machine, but like I said, you could have multiple machines with sensors installed, and then you come with the LiveView Mobile and measure periodically the partial discharges here. Additionally, you can also measure the rotor flux and shaft voltage monitoring, as well as for the PDA2 previously that I did not mention, which I'm going to explain a bit further away. So instead of the continuous monitoring that gives you data every few hours, this will give you a snapshot of a discharge pattern at the time of testing. So then depending on how often you do these measurements, you're going to have, a history of the discharges. And the results are essentially trended against previous reports, like I showed you in this real case situation. Oops. All of these solutions come together with a software, with an analysis software. So first of all, this software is going to show you the partial discharge patterns on the left side, and then also the trends on the right side. So essentially, this is what I mentioned at the beginning, what should we be monitoring. And with the software also, it has some increased additional analysis options to look at previous history and different types and of analysis options possible to investigate how the patterns look like. So this would be a typical installation of a PDA2, so the monitoring equipment, or you can use a mobile equipment. You have your rotating machine. Through the terminals, you connect sensors. Through the protective device, the signal then goes through, and then it goes to the monitoring equipment. On site, it looks something like this. So you can install it somewhere next to the machine, maybe on the wall. The only limitation here is that you should try to keep it as close as possible to the sensors in order to ensure that the signal, the good quality of the signal goes to the monitoring equipment. Then quickly about offline monitoring. So to remind you, offline monitoring would happen when the machine is switched off. So you would need a different tool. So what we offer here is 2 types of tools, the LiveView QTD and QLF. So this can be used as well for multiple machines. No sensors would need to be installed previously. And it also incorporates some additional parameters to be measured, such as the tan delta, the polarization index, and insulation resistance. And yeah, this would be also a portable tool that you could carry on for multiple machines to test them. QTD is essentially part of the planned maintenance program. So the complete kit would perform offline PD measurements and the tan delta measurements. The tests would be made with an external power source that must be available at the site, so at 50-60 hertz, and measurements up to 20,000 volts can be actually made. So yeah, as I mentioned previously, you would get a similar PD pattern. You would get, again, trend values to compare with the previous measurements. However, these PD patterns and maybe the magnitudes would be different from online because we're measuring a little bit different conditions. So mainly it's from the electrical stresses. But offline measurements give you a better option or possibility to pinpoint the location of the problem. So once again, this should be used complementary both online and the offline solutions. On the other hand, we also provide a very interesting solution that we call the very low frequency measurements. So at 0.1 hertz, the whole kit already contains a high voltage source. So the measurement kit, the laptop, and the high voltage source altogether would be around 50 kilograms. So it would be quite easy to transport to sites. It also has the polarization index and insulation resistance testing available. And you can also make measurements up to 24 kV. So this is a bit more portable solution because you don't need the external power source already in the plant. You can bring your own. And then there's the combination of both that we call the QTD LF, which combines the advantages of both the QTD and the QLF. So the possibility is to measure with this low frequency source at 0.1 hertz. And also, if you have an external power supply, you can measure at 50 or 60 hertz. So I talked about all these measurements and how do we analyze the data, and that of course you need sensors to capture this data. So let me show you the types of sensors we actually have for partial discharges. There are essentially three main types. So first one is the coupling capacitor, the second type is the current transformer, and finally you have the Rogowski coils. So they're designed to work on one particular phase. So you only need one sensor per phase on a motor or generator. And there's the options for essentially three different cases. Normally, most of the machines, if it's possible, we would suggest installing the coupling capacitors, so the ones on the left, depending on the rating of your machine, so up to 12 kilovolts, 17, 34, we will install different types of coupling capacitors. These coupling capacitors act in a way that they filter the 50, 60 hertz signal, so only the high frequency signal, that is the PT discharges, will be let through. And there's also inside a voltage divider that will scale down the voltage, so we only output a very small voltage to the analyzer, so to the PDA2 or, for example, the mobile kit. On the other hand, if the machine already has an installation of surge capacitors, so the coupling capacitors would not work that well, then we suggest installing the current transformers. So in the middle of the current transformer, from the surge capacitor, you have your earth cable leading to the earth, and on this cable you can install the current transformer. So the current transformer essentially would work as an inductive sensor. So the more current goes through it, the higher the signal it will output to the analyzer. And finally, Rogowski coils are specially designed to be used in the EX environment. So a bit similar to the current transformers, it's an inductive source. You have an air core inside, you have a coil inside, and then once you see fast transients, so fast partial discharge happening, then the Rogowski coil will convert it to the signal for the PDA2 or mobile kit to analyze. And just here to show you some typical installations. So on the left side, you can see the current transformer installation. So you can see that the wire is going from, so the green-yellow wire is going from the surge capacitor through the current transformer and then to the earth. And then from the current transformer, there's this red marked cable and yellow marked cable going for each of, for the two phases. And this cable then goes to your analyzer, your PDA2. In the middle, we can also see a typical installation of a QCC12. So next to the terminals for three sensors for the three phases. And finally, on the right, we can see the Rogowski coil installation. So Rogowski coils can be installed either around bushings or high voltage power cables. So depending on your machine, depending on your requirements, on the conditions and the accessibility as well, there are multiple types of sensors we can install. So if you have any questions or concerns, you can ask the distributor, you can ask Tiara on the suggestion of what type of sensors would be the best adapted for your particular type of machine. So now we covered the main part about condition monitoring of the partial discharges and the types of online and offline monitors, the sensors, and this was all essentially connected with the stator winding tests. But as you remember, in one of the first slides in the beginning, I also showed you that the two other main types of problems that happen in machines are connected either to the rotor windings or also the bearings and the shaft. So let's look at the next characteristic we can monitor, and which is called the air gap flux monitoring. This solution is developed and intended for turbo alternators for two-pole machines. It allows us to detect inter-turn faults. So we can detect shorts between the turns in the windings. So for your coils, you have a winding like this. And depending on, the age of the machine, depending on the condition or maybe some contamination, you can actually have a short between the windings. So this is, again, non-invasive diagnosis. So it enables to detect the fault without dismantling the machine, same as for the partial discharges. It also allows you real-time monitoring, so continuous health assessment during the operation. And for this, what we suggest is that the measurements need to be made online, and the condition should be established online, because it can be that the interturn shorts only appear when the machine is on. So once there is centrifugal force, so only then some of these issues can appear. So how do we measure magnetic flux? On the right, you can see the rotating machine and a sensor placed on the stator. And you have the two poles, and essentially each of the coils go through the sensor one by one. What we can do is we can measure the leakage flux, and for working insulation, this will be one value. However, if there is a short, what we're going to see is less flux going out of the turn. So if you compare it between two different coils, and you can see that one of them is lower than the other one, it is an indication that there is a problem in the insulation, and then most probably there is a short. So now if you look at this rotating right part and keep it in your mind, I'm going to show you how the actual measurement looks like. So don't be scared here. The red part is the voltage measurement. So each of the coils has a particular peak. So once the sensor goes past the coil, there's a peak. Once it goes, the next one, there's another peak. Once it reaches the pole, there's going to be a bit flat line. And the blue part is the flux, which is just an integral of the voltage. And the green part, I'm going to explain a bit later on. This is essentially which of the coils is uncovered or more sensitive to this measurement. At different load points, different coils will be more sensitive to make the measurement. And what happens here is that you just compare, the coils from one pole from one side to the coils of the other side. And you compare if the difference in the voltage or in the flux is high. If there is a high difference, it most likely means that there is a short. And to explain you a bit about the sensitivity of these measurements, bear with me here, a bit technical, a bit of engineering. So we have flux experienced both from the armature, so when it turns, and then there's also flux, the main flux from the rotor. And what happens is that both of these fluxes are actually aligned when there is no load. So it's sometimes a bit hard to detect this leakage flux from your coils in the rotor because there's also the flux from the armature. So once there is no load, these magnetic fields are nearly aligned. There's no difference between them. However, so this is rotating, and then it's a bit harder to get the data. However, what we can do is we can open the turbine valve a little, essentially increasing the steam flow and the mechanical torque. And since the generator is locked to synchronous speed, the rotor cannot spin faster. So what it can do, it can just shift a little bit ahead by some load angle that is called delta here. And then essentially this uncovers some of the coils for higher sensitivity measurements. So once you do your condition monitoring, it is better to do this monitoring while you go through different loads, because then you are more sure and certain that you're going to uncover a coil and have a more precise measurement. So to give you an example, here you can see the graph of the active load versus reactive load. So at different points, a different coil will be more sensitive for measurements. So once the load is here, you uncover, for example, coil number 2. Once the load is increased, you will uncover coil number 4, and so on, and so on, and so on. To give you an example, also how it looks on the software. So here it is on the generator with initial load of 5 megawatts. So there is a small phase angle. And what you can see here is that the orange line is going through the coil number 6. Once we increase the load, the orange line now goes through coil number 5, 4, we now increase load even further. 3, we increase the load further. 2, and 1. So ideally, once you do the condition monitoring of your flux, your coils, you would go through different loads to uncover different coils for higher sensitivity measurements. If this is not possible, and you stay at the same load, this is not critical or dangerous. It's just that the sensitivity of the measurement is going to be a little bit lower. So how does a fault actually look like? So here, there's again a scenario where coil number 2 has been displaying lower voltage on one of the sides than on other sides. So what you can see here is that if you superimpose this part, if I look at like this, we straighten it up and superimpose it on top of each other, we can actually see what is the difference. And here we see that there is a difference of around 40% between the two coils, which means, assuming we have 10 turns per coil, it would mean that probably 4 of the turns are shorted. So it's a very quick and easy diagnostic by just looking at the differences between the two sides of the generator on the 2 different coils. So it's quite fast and quite easy to capture if you have inter-turn faults. And just a bit of a zoom in, yes, to what I explained previously. To sum it up, monitoring the magnetic flux will help you determine shorted turns on the rotor. So as you can see on the image on the top right, the installation is quite straightforward. You have one sensor, so a coil measuring the flux. You install it in the slot, and then, in the wedge. And then once the machine starts up, you're going to measure each of the coils. And as I showed you in the software, you're going to see these peaks, and these peaks can be compared to each other to see if there are any short turns. And finally, the third part of the measurements is the shaft voltage monitoring. So this is for the health of the bearings, for the health of the shaft. First of all, the question is, what causes shaft voltage? There are 3 main types. So electromagnetic, so maybe some static eccentricity in your machine, some misalignment that puts one part at a higher voltage than the other part. You can also have electrostatic, so a charge buildup through some friction, through some belts, or maybe through some water droplets. And also you can have the external voltages. The question now is, what happens if there is an increased voltage on your shaft? What we're going to observe is bearing currents. As the shaft voltage grows, it will have a charge buildup on the shaft and nowhere for this charge to escape. And for it to escape, it will try to find the path of the least resistance. And what it's going to do, it's going to find it through the bearings. Once it overcomes the dielectric film of the bearings, the current will start to flow through the bearings. And what happens here is that you're going to see real mechanical damage. So as you can see on the pictures on the right and the bottom, you have this kind of like fluting, and essentially you're just making like mechanical grooves, or even, big holes like this. And this can lead to some really catastrophic failures if your bearings essentially stop working mechanically. The issue here is that it's not possible to directly measure it through the discharges, but what we can do is we can monitor the shaft voltage and also the grounding current. Also, on most machines, there are already some countermeasures introduced. So you can have passive filters to eliminate the external voltage. You can insulate the coupling between, for example, the driven equipment and your rotating machine. You can insulate some of the bearings, but the most effective, I think, at this moment, and probably the industry standard, is shaft grounding. So you install either some kind of a shaft ring or maybe a shaft brush, and then connect it through a cable or through a strip to the ground. And you can also insulate one of the bearings on the other side. So this is kind of the best countermeasure at this moment, and probably, like I said, the most popular and widely used. However, my question here is, how do you know that your countermeasures work? First of all, your grounding brushes are prone to accumulation of dirt and wear. So at some point, your grounding brushes are not pushing on the shaft as much anymore. and less of the current is actually diverted. You can also have issues with the poor or no contact of the earthing cable or the earthing strips. Maybe after some intervention, it's not put back on. You can also have insulation breakdown on some of your bearings, or maybe something has happened with your machine. There is new imbalances in your rotating machine, and this will give rise to shaft voltage. And maybe your current setup of the shaft grounding is not enough to essentially divert all this new shaft voltage and current. So our suggestion here is to use additionally a sensor that tells you what is the shaft voltage. So, and also you can measure some current going through the earthing cable. Once you establish this, you can monitor if the voltage grows or it stays the same, and it gives you an indication of both health of your machine, and second, also the health or the performance of these countermeasures I showed you in the previous slide. So you can maybe see that you need to change your grounding brush because, you know, there's too much wear, or maybe you need to clean the shaft because, you know, there's too much dirt accumulation that the grounding brush cannot work anymore. And what we provide is, again, multiple different solutions depending on the machine. If there is already insulation, where the access points are, we can install one sensor on the drive end, we can install one sensor on the other end, or we can install two sensors on the both end if it's available. And then depending on this, you can make the analysis of the health of your shaft. So in general, high shaft voltages might lead to bearing damage. To monitor the health of your machine and monitor if your countermeasures are working, we would need to install additional sensors. These sensors can be used with online monitoring solutions that Quartzteq is providing. So you can do both the shaft measurement, flux measurement, and PD measurement with the same type of device. And finally, if those who remember that with the PD part, I was telling you that by looking at the PD pattern of the partial discharge pattern, you can actually establish what kind of fault you have. The same thing is applied to shaft voltage. So not just by looking at the signal, but by doing a frequency analysis, a harmonic analysis of your signal, you can actually find that, for example, you have a static eccentricity, a rectifier fault, or maybe some rotor interturn shorts. So it gives you, again, another data point so you can plan your outages and your repairs much better. And then, yeah, for the last part, I want to tell you about the system integration. So as you now know, all the three possible measurements, so the shaft voltage measurements, the flux probe, and also the PD measurements, they all can be combined on one machine through some safety connection boxes. They can be connected to your measuring device. So in this case, it's the LiveView PDA, which is your measuring device. It collects all the data. It can do some rudimentary analysis, show you trends, show you patterns. But then the question is, you also want to export this data, right? You want to either to show it somewhere else, or you don't want to always go to the analyzer to see what is the status of your machine. For this, there's a lot of integration options. You can install Wi-Fi and connect it through Wi-Fi. You can connect it through a local area network through an Ethernet cable. There's also the possibility of integrating the signal of the 4 to 20 milliamp analog outputs or relay outputs to your existing third-party systems, such as SCADA. You can also use Modbus TCP. So once again, depending on your needs, depending on the existing infrastructure, on the existing systems, there are many possibilities of how we can integrate these online measurements into your existing systems. So it's not that, you need to build something completely new. And for sites and places where you have multiple generators, multiple machines, it's also possible to oversee them again as one. So you could have some local PC server dedicated to monitor all the different equipment you have. Once again, different types of connections, local area, Modbus. Again, you can ask us or Tiara for the suggestions with your needs, and I'm sure we can find a solution how to integrate these systems in your existing systems. So this is the end of the technical part. I hope I did not bore you, and there's a lot of interesting information for you to get. But as we still have time, I see around 9-10 minutes, I actually want to do 2 case studies. two real cases how condition monitoring has helped our clients in the past. Those of you who paid attention know that for the PD analysis, we need to look at three main things: the magnitude, the trend, and the pattern. And we can use this partial discharge as a monitoring tool to tell us about the state or winding health. And just for you to remember as well that doubling of the magnitude over a year, gives you an indication that there's some significant deterioration. And then pattern recognition can also give you the help to understand what remedial work needs to be done on your machine. So you can match the discharge type to the problem you need to fix. So case study number 1. This is a machine manufactured 2015, 11 kV machine, 2-pole. What was done on a minor inspection was that it was uncovered that you have this kind of like white residue inside the machine. And this is an evidence of the PD activity. So this is an evidence of ozone. This is an evidence of chemical reactions. So we know that there is some type of partial discharge activity actually happening in the machine. So now the question is, do we need to rewind it completely, or maybe we can do minor repairs? And what was decided based on the magnitude and of these first measurements was that it's not that critical yet. However, some remedial work needs to be done. So what was done was, like I told you before, that for some of these partial discharges on the surface, you can just truly clean it, which should decrease the amount of partial discharges. It was then coated with epoxy resin to reinforce some of these loose winding components. And also it was painted with anti-tracking paint, so to decrease it, even further after it was cleaned. And to give you an idea of, how the partial discharges can help you determine the health, first of all, we show you the initial testing. So initial tests showed you that the QM value, which is the characteristic value, so you can see it on the top left here, was 4.6 nanocoulombs. It's not great. It's not horrible. It's somewhere in the middle. And this is what we saw also from the visual inspection. And after we did all this remedial work, the cleaning, the application of this anti-tracking paint, we did another measurement. And this time, the PD discharges decreased by a factor of 8. So from 4.64 to 0.8. You can see here that the scale here is completely different. So this scale is 4 times higher on the left side. So it's around above 40. And on the right side, the scale is 10. So the partial discharge is decreased by a factor of 8, which means that the health was really improved of the machine. And now, probably, for the next few years, no additional work will be needed because these partial discharges are a very, very low level. What was then also done was that PDA2 was installed. So to do these kind of monitoring more regularly, previous equipment was shown to not be detecting these kind of PD discharges. And what was now happening is that every 3 months, or you can do it every 6 months, the data was sent to be analyzed, so to catch these issues a bit faster. But as we saw now, the partial discharge trends kept quite low. Okay, and then for the last one, the case study number 2, this is a lot older machine, 1990, I think also 11 kV machine, 4 poles, 50 hertz. On the outage, machine condition was assessed. There was a visual inspection and also preliminary testing. And what was discovered was that there's a lot of spark erosion. So a lot of partial discharge activity must have happened before, so that visually it was already detected. So in our opinion, this is already a bit too late. Once you do the outage and you see that the damage is so high, it's, the condition monitoring could have prevented this. They did offline discharge, partial discharge test. They saw quite high values and also this kind of indicative cloud forming above the internal PD level. So this means that there is some kind of a gap discharges happening. So something more serious than just some small internal discharges. They also did a darkroom test. So here, maybe there's a zoom in. yes, there's a zoom in, so they saw these discharges happening in real time, and they saw the extensive damage already done by the partial discharges. Here, results were discussed with the customer, and it was suggested that the machine needs an overhaul. However, against the recommendations, because of the production demands, it was put back online. And at least the PDA2 was installed to kind of keep monitoring the health. And here I can show you the real benefit and the strength of this online monitoring, of permanent online monitoring. So the machine was put back on, and this is how the trends start to look like. And if you see on the second screen, the white part is increasing very, 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 like an exponential, very fast. And here, what you can see is that for a couple of days, it kept increasing until some very last week. It was like a huge shot up, essentially, on the partial discharges. And I think in the next slide, it actually tells you that, yes, so we managed to see stable trend for 4 days, slow increase for 18 days, already a bit of, it's quite fast. And then finally, in the end of May, yeah, for 5 days, there was a very, very rapid PD increase. And this, when the decision was made that the machine needs to be stopped, because it would have been essentially a catastrophic failure. So yeah, altogether 28 days after this first intervention where we saw this extensive damage and then started to monitor the PDs, after 28 days, we had enough data to say that no, and we managed to convince the client that the machine needs to be shut down. Otherwise, there would be failure. So in the second outage, they dismantled the coils, showed serious damage to the semiconductive coating and visible core corrosion. And full rewind was recommended and undertaken. And fortunately, in this case, that we managed to install this condition monitoring device, we managed to prevent catastrophic failure. So this is it from my side. I think hopefully right on time. I just go back to my last slide. Thank you everyone for listening, and I think if you have any questions, I'm happy to take them.
Oke, thank you, Chris.